Hello, everyone. Thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on EMA3D Cable 2022 R1. Before we start the presentation, let's review the user interface. On the top of your screen, you will see a bar with 4 options for you to click. To ask questions, please click and open the Show Conversation option. This will show the meeting chat, and this is where you may ask any questions you have during the presentation. At any time during the presentation, you can submit your question. Your question will be placed in the queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. Now on to today's speaker. Tim McDonald is president and co-owner of Electromagnetic Applications, where he has implemented new system modeling approaches to simulate the interaction of systems and their electronics with electromagnetic environments in a shorter time with more accuracy and at a lower cost. Tim currently serves as product manager for EMA3D Cable. He supports EMA3D Cable users around the world from multiple industries. Tim previously led consulting engagements for NASA and DoD major primes pertaining to specialty engineering of critical systems, development of novel solutions to electromagnetic compatibility problems, and in the execution of major programs that require verification to electromagnetic environmental effects. Without further delay, I will pass it off to Tim to get us started.
Thank you very much, Kaylin. I'm very excited to be here today to talk about the new updates. It's been a fantastic year for EMA3D Cable. We've expanded our product to customers really all around the world, and it's been a great year of showing the capabilities of the tool and pushing it into new frontiers. On the EMC front, we've been able to show with EMA3D Cable that entire EMC measurements, reverb chamber measurements, anechoic chamber measurements, broadband up to from the low megahertz up to 18 gigahertz are possible and computationally feasible. But more importantly, that our tool allows engineers to build these models in a fraction of the time of other tools. And today I'm pleased to announce the new features that we've been working on in the last 6 months that are rolling into the 2022 R1 update, available on the ANSYS customer portal or through the ANSYS channel partners. So the product EMA3D Cable, it is a device level or platform level electromagnetic modeling solution made to attack the hard parts of developing models from mechanical CAD and extending PCB and antenna modeling to include full devices, cables, as well as platforms. And today I'm happy to announce our number one requested feature ever would be to add a transient co-simulation. So we now can solve arbitrary transient models self-consistently with EMA3D. I'm going to talk about that more today. First, let's remind ourselves what EMA3D Cable is for. Many things, but mainly we'll be talking about the EMC or EMI development process. So typically we start by designing a device using PLM software, CAD software, and other means to pick our design and get that into a prototype, eventually fabricate a qualification unit for EMC compliance testing in an anechoic or reverb chamber, and then after success, move into production. However, in recent years, through a lot of work and a lot of advances, we've added a new phase in the development process. After device design, we can take our mechanical CAD, we can take our ECAD, and we can do an EMC simulation phase and then an EMC mitigation phase. That means we don't have to wait until compliance testing to make changes to our design. In the past, EMC simulation was considered expensive, impossible, impractical. It was a research project. But now with EMA3D Cable and new advancements in CAD, PLM, and ECAD processes, we're able to build accurate digital representations of the EMC performance of devices in a fraction of the time that it took before. So let's talk about the distinguishing features. First, the solver for EMA3D Cable is accurate. It's been built and developed at EMA for the last over 30 years. It's a full wave solution of Maxwell's equations self-consistently with wire harness simulation. Now I say wire harness simulation, it began as a transmission line solver, but has evolved to a general wire, shield, branch. All aspect of cables can solve in a reduced dimensionality solver that co-simulates self-consistently with the 3D solver. And new today, I'd like to announce, we now have the ability to have an integrated co-simulation with the ANSYS Nexxim Transient Solver. That means that every step of the simulation can be solved in 3D and the Transient Solver and in the circuit simulation, all at the same time. So we've added this in such a way, and you'll see in a moment, so that we're within the ANSYS Space Claim interface. It's intuitive for new users. It enables the use of mechanical CAD directly with minimal cleaning or preparation, so that users can prepare models of complex platforms in a fraction of the time of other methods. And of course, we're integrated with the workflows of ANSYS SI-Wave and HFSS, so that we can pull in fields predicted on antennas or PCBs and simulate the effects of the cables in the enclosures in a short period of time. Okay, let's talk about the 2022 R1 updates. So the first I've already announced, we'll talk more about in a moment, is the EMA3D and Nexxim transient circuit co-simulation. So it'll allow us to model complex devices and platforms all the way down to the circuit level and reduce our time for simulation by more than 10 times. In addition to that, we've got a new material and cable libraries so that users can save the materials or cable cross sections that you've developed and pull them up at a future time in a different model. You can share them with colleagues across your company. And finally, we've expanded cable harness connectivity features so that you can do things that really take our cable harness solver to new levels. So that includes the ability to break conductors out of shields and completely control the connectivity of all the conductors, all the shields, so that we can see the effects of connectors and where cables are terminating inside of electronics boxes. Okay, let's talk about what these features are for. So designers are looking for ways to predict their EMC compliance of their products early in their design phase before they get to the prototype phase, because that's part of the EMC development process that's expensive. Prototyping, taking it to testing, potentially failing that test and having to do a late phase design. Testing does not always reveal the cause of a failure, and it can occur at a late, expensive period in the development cycle. And we need to deal with complex 3D geometries, cables, and circuits, all co-simulate at the same time. So the capabilities that we've added now is the ability to co-simulate with Nexxim Transient. So we've got a non-linear circuit elements may be possible. We can add in things like diodes or other non-linear components to self-consistently co-simulate. We've got the ability to model complex material property descriptions and cable constructions that maybe can take some time to put together and research. They can now be saved in a library, so you can pull them up and reuse them with ease. And we've got more realistic cable and shield terminations that can be modeled with the expanded connectivity features. And these new features taken together help us put together and model complex scenarios 10 times faster than competitive tools. So the benefit is you turn EMC simulation into something that's not just a research project, but something that can contribute to a program's development cycle. You can add things like filters, circuits, ESD diodes, lightning Zener diodes. All of those components can be added in with confidence, and then we can iterate through mitigations. Those mitigations may be at the circuit level, they may be at the cable level, or at the 3D component. So you're going to save money, but also save risk. You'll go into your EMC testing with confidence that you're going to pass and shorten your development cycle and the churn between engineering groups. Okay, let's talk first about the Nexxim transient co-simulation. So we have two existing solvers, EMA3D and M-harness. They together can now co-simulate with a third solver, which is the Nexxim transient circuit solver. So as always, users will specify the 3D geometry for EMA3D solver, and it can be complex geometry, frequency-dependent surfaces, anisotropic surfaces, thin surfaces smaller than the cell size. You can use the scene joint algorithm, everything you like and know about EMA3D and its ability to quickly work with mechanical CAD. Added to that, we've always had this, the ability to model complex cable harnesses with our abstracted representation where we specify separately the path of the cable in 3D and the composition of the cable cross section. And then what is new is we can click on any of those cable terminations and we can now add a complex Nexxim circuit as a termination to that cable. And then when we're ready to run the simulation, all three solvers, the Nexxim circuit transient solver, the cable harness solver, and the EMA3D geometry 3D solver, each co-simulate together time step by time step for self-consistent simulation. So adding a Nexxim circuit termination is as simple as clicking the circuit termination for a complex circuit termination in the ribbon at the top of the screen. Then users are asked to select where in 3D, which cable path they would like to add the complex termination. After that, the cross section of the cable pops up and the user just clicks one or more conductors that will be part of the circuit. And then after that, it pops up to show the selected ports that the user selected, as well as a typical circuit layout that users can wire with various components. So I'm going to show what that looks like live. So we've got an aircraft. That aircraft has an overbraid, twisted shielded pairs, and a coax inside of that cable, and that's at a specific point in the aircraft. So we just click the complex circuit termination tool. We click the wire, we click the end of the wire that we want, and then we choose the layer, in this case the third layer, and we select one or more of those pins where we would like to have that complex circuit. So in this case, we can actually select three, the coax center and then two TSPs. So now we can select from lumped elements, we can select nonlinear elements, we simply drag them over to the sheet. We can rotate them, we can add grounding points anywhere we would like in the schematic. In this case, we've added a ground location. The twisted shielded pairs are cable 4C0 and cable 4C1. And then our coax cable is cable Nexxim. So in this case, we can add a simple pi filter on the end of this twisted shielded pair, which will essentially serve as a low pass filter to attenuate from the high side to the low side of this particular circuit. So again, we're taking our design a step further, whereas previously we could look at the 3D geometry and the cable harness geometry. There was no ability at all to wire up connections like we're seeing in this demonstration. So now we're going to wire up this pi filter, and we'll be able to run this self-consistently with the aircraft and the cable harness itself, so that we can determine in a holistic manner how energy couples through the aircraft and how we have solved or not solved our EMC issue that we're working with. So we're just going to wire that up to ground and then wire that to the other side of the twisted shielded pair. And then we've got to wire up our coax cable to ground. and then we're ready for simulation. That's all it is. Now it's bundled into the software. We can plot the induced voltage or current on that line with that circuit termination. Okay, let's talk about our next update, the ability to export and create libraries for material properties, as well as cable cross sections. So we all know that EMA3D cable materials are complex. They may be frequency dependent, anisotropic, or have other complex details. In addition, when we're building cables, we may have harnesses that have multiple shield levels, braided or foiled, multiple conductors, twisting, certain twist pitch, and a variety of dielectric fills and wraps. Now, both properties as well as cable descriptions can be saved for reuse or shared with colleagues as XML files. So first, let's look at the material library. So we've got a particular property. There's a new export button. So when we click that export button, that carbon fiber composite gets loaded to the library. So next time I go to the library, I can select carbon fiber composite directly. And if we look in my user hard drive location, there's a XML file that contains all of these user-defined materials. I can share those files with colleagues and they can add them manually to their library so they don't have to come up with all the details for that property. Okay, we can also do the same thing for our cable export library. In this case, this is maybe an Ethernet cable that I've spent quite a lot of time designing all the TSPs to have the right gauge, the correct wrap, foil shields, as well as the braided shields. Everything's the right gauge, the right twisting pitch. We can now save all parts of that cross section as a cable. And that allows me with one click to assign all of those various conductors. You can see there's 4 shields, 8 conductors as part of the pair, and a ground conductor. I don't have to assign those point by point with a click. I've got the ability to save that entire cross section as a quote unquote Ethernet cable and pull that in and assign it whenever I need to. Okay, next, let's talk about our expanded cable harness connectivity features. So we're excited about this. So EMA3D cable, the flexibility that we afford users now in terms of our ability to have branches in cables, our ability to have multiple shield levels. That's always been a distinguishing feature, but that's only really helpful if you can break the conductors out of those shields in order to terminate them to real PCBs. So with these expanded connectivity features, users now have the ability to do more and more. So we've got a variety of complex terminations. So we can have conductors break outside of shields. We can have the electrical impedance of multiple topological shield levels be specified by users. We can now have high impedance shield terminations or disconnected shields, which is something that happens in the real world with real world products. We now can accurately model the coupling of those open shields where they're not electrically grounded in the 360 manner at the end. So competitive products don't have this ability to specify conductors through these topological levels and have all the variety of different ways to terminate the cables. So if you right click on harness under configure harness, there's some new options, the ability to override the connector type, and you can see there's open and closed options. When open is specified and we have a moderate or high impedance termination on the cable, that cable will be slightly defeated. So the fact that there's a higher impedance means current can flow and fields can couple into and under that shield. Topologically, it's broken. So that happens in a real cable. There are real effects to a poor termination of shield, and we can capture them in an accurate and a consistent way. There are some times when you don't want that behavior. We have the ability to close those shields. An example is when we're putting a port on a shield in order to capture the behavior for an S parameter extraction. In that case, the 50 ohms or 100 ohms, the port impedance is not a real impedance. It's there to help us capture that port effects in the S parameters. So we don't want our shield to open up when we're doing S parameters. So by default, EMA3D cable will be closed when users are doing S parameter simulations. This override ability gives users some control on whether this feature is utilized. Okay, conductors can break outside of shields. So this is critical. In order to connect everything and have it be like a real product, you have to be able to break out of shields. In this case, we've got two patches that are parallel to each other. The upper patch is connected to the inner conductor of the coax. The lower patch is connected to the shield of the patch on both sides. So with EMA3D's new features, we can control the impedance and break the center conductor out at that junction. It's very simple to specify. Just by clicking the additional lines, we can do that. And the connectivity can be specified with a couple of simple clicks. But it's a very powerful tool and lets us do some real engineering for actual terminations of cables. We've also got the ability to have conductors where the shield just terminates in air. In that case, we've got a new surrounding material termination type, and that surrounding material may be air or something that's high impedance. When we do that, we can have shields just terminate in air. And this happens sometimes. There's real applications where shields are not perfectly terminated or low impedance terminated at the end. Now we can actually accurately capture those effects. Okay, let's talk about some additional updates that are not one of our 3 featured updates, but may be important for many users. We've got performance optimizations to the Mesh Inspect tool. So this allows us to mesh entire electronics enclosures. For example, entire cell phones, entire computer enclosures. We can visualize these complex meshes with the Inspect Mesh tool, and now what used to take minutes, many minutes to visualize, now we can see in just a couple seconds. We've added the ability to import near field sources. So we've long had the ability to pull in fields from HFSS, from SI Wave, or from other near field scans. We've now added yet another format, the NF1 specification. Next, we've now bundled our Linux EMA3D solver. Many users want to run on clusters that are Linux clusters. Well, SpaceClaim GUI is not available in Linux. The EMA3D solver is available in Linux. So users can get access to the Linux installer in the main EMA3D Windows installation. It's there in a zip file during installation, as well as the instructions. So you don't have to go hunting for that. It's right there when you download EMA3D. So we've added some pop-up GUIs to quickly visualize the cross-section of cables, and we can even copy that cross-section. We can copy and paste a complex cable description with all of its shields, all of its conductors, gauges, pitches. And when we paste it, all of those conductors and shields get copied with it. And so that's a very nice feature to speed up model creation. We've added a search bar to the simulation tree so we can filter out by name and allows us to very quickly see what we've got in a complex model. We've made numerous user interface enhancements, added support for the delete tool, and selecting multiple elements at the same time. We've updated the meshing engine to support arbitrary radius cable deconfliction so that users that are meshing with cables, the cables themselves should not overlap each other. So now the mesh engine can automatically try to avoid those overlaps. And we've added thin wire structures in 3D, which we've always had cables, but now we can have thin wires. And that's especially helpful for models where the mesh grid settings are different spacing for X, Y, and Z. And finally, we've got a new tool to find 3D voltage sources. So we've always had cable voltage sources. Now we can have voltage sources in the 3D geometry. So let's talk about how these 3 new features, and all the features are helpful in different industries. So let's start with electronics and consumer electronics. So in this case, we've really expanded the use of EMA3D to cell phones and electronic enclosures. As I mentioned, we can model a full reverb chamber up to 18 gigahertz. We can model an entire computer enclosure up to 18 gigahertz. We can model an entire cell phone up to at least 18 gigahertz, probably much higher. And we can specify EMA3D to pull in and mesh the mechanical description of that cell phone. So the geometry doesn't have to be cleaned or prepared. It can be very rough geometry, and we're able to model it. So we can model EMC, we can model descents to see how we're affecting antennas, or antennas are coupling to electronics traces or cables on that PCB. So you can see the example of how detailed things like PCBs, as well as designed antennas inside that cell phone, can be modeled and the effects captured with EMA3D. So obviously we have great tools for simulating PCBs and antennas, but EMC is more than just a PCB levitating in a vacuum. When we do EMI EMC, we have enclosures and we have cables. And so the effects of shields and their termination, the effects of the enclosure vent holes and fan holes, the seams and joints at the lids, whether they're gasketed or not gasketed. We may have EMI absorbing tapes or cable chokes. So really, EMA3D cable gives us a method for scaling up from just PCB and antennas up to more complex geometries. And by being able to pull in fields from other tools and to quickly mesh the geometry, EMA3D is a huge time saver. Okay, an EMC environment that we can handle is electrostatic discharge. So with EMA3D, we can handle the time domain transient. We can couple discharges to cables and see how the ESD discharges couples through cable shields. We can see how ESD couples from the outside the enclosure through apertures inside of an enclosure. We can see how ESD couples to PCBs and to individual nets on PCBs. And we can take that all the way down to the circuit level with a new Nexxim solver. EMA3D is now perfect tool for radiated emissions product design. We can pull in fields from SI Wave or HFSS for PCBs. We can model the performance of the PCB enclosure, the fields from SI Wave, the fields created from cables, and see the superposition of all those effects on top of each other. And we can also do signal and power integrity and consider the effects of the cables and connectors. So we can do an S parameter extraction from any cable and connector in EMA3D and wire that up in a circuit model for our follow-on signal integrity, power integrity analyses. Okay, let's talk about radiated immunity. Last year, EMA3D added the ability to do subgrid modeling. So this allows us to look at radiated immunity and couple those threats down to PCBs and other very small components. We can do multi-levels of fidelity and handle the effects, the susceptibility, the immunity effects of an exterior illumination. Finally, we can do cable and connector transfer impedance analysis. So we can model transfer impedance, we can predict transfer impedance, which is an important metric for cable manufacturers. And conducted emissions and conducted immunity. By coupling together the circuit solver, we now have a fantastic package for CECS. EMA3D cable can handle the inductances, crosstalk, and stray capacitance of the transmission line, and we can model the front end filters of the circuit with the Nexxim Transient solver, and taken together, all of it together gives us one self-consistent CE, CS, or CI solution for looking at coupling. Okay, let's talk about how these new features are important for aerospace. Again, in aerospace, our environmental requirements are specified at the environment level. Lightning, high intensity radiated fields, or HIRF, as well as electromagnetic pulse, or EMP, are specified outside the aircraft. It's up to the applicant to determine how those fields couple into the aircraft to the critical electronics. EMA3D is a tool that can perform that coupling and reduce or eliminate the need for full aircraft testing. So for lightning indirect effects, or E3, now with the added Nexxim circuit solver, we can model the circuit all the way to the end. So we can add things like TVS diodes, Zener diodes, and we can see whether or not we've sized those diodes appropriately for the transient that is coupling to them. For HERF and EMP, we can add our filters, and we can see if the capacitors, inductors, and other filter components that we add to the front end of our circuit are appropriately handling the HERF and the EMP pulse itself. As we look at fuel tank ignition prevention, our ability to save anisotropic materials will be critical for complex tank designs. For DO-160 qualification, again, we can determine whether or not our Zener diodes are protecting from ESD. We can see if our diodes are sized properly for lightning. We can take from the box level to the circuit level and see if we've got the correct design. Okay, radio frequency interference, or RFI. With EMA3D cable, when you're in a reverberant cavity that's electrically large, that can be challenging for other electromagnetic simulation tools. So EMA3D cable is very helpful for looking at coupling in large reverberant cases. In addition, sometimes antennas couple to each other through the cable itself. So when you have the cable, coax cable that's connected to the RF port is the source of interference, that's a case that's not easy to analyze with other methods. So EMA3D cable can be an important part of RFI when combined with other tools. So for example, EMA's ARMS measurement system allows for the measurement of arbitrary receivers and transmitters with a dramatic reduction in the time for testing. We need to know what the susceptibility level is, or the transmitted out of band emissions quickly. So ARMS helps us understand what the equipment is like. EMIT is a tool that integrates data from the disparate tools to determine whether or not there's risk for upset. HFSS is a tool that determines the coupling between ports. So EMA3D cable slots in this workflow to help determine the coupling when it comes through a cable, and also help us model some cases with resonant cavities that are hard to analyze with other methods. Okay, let's talk about how the new features in EMA3D cable are helpful in the automotive and industrial industries. Again, we need to consider our full vehicle. As we move toward electrification and autonomous vehicles, we have new EMC requirements. When we have electrification, we have more aggressive sources from those electric components. In addition, safety critical components require by government regulation EMC compliance testing. Autonomous vehicles have more safety critical electronic systems. So the amount of testing required has been growing dramatically, while at the same time the amplitude of the aggressors from electrification is increasing. So we have brand new challenges. So we have to be able to predict EMC at the vehicle level. That in the past has proven challenging, but with the forgiving meshing and the co-simulation with cables and circuits, it's now possible in EMA3D cable. So let's talk about ESD, a required environment. We can model all the way up through the cable to the vehicle itself for the ESD coupling. For radiated emissions, it's very similar to what we talked about before, but this can be done at the vehicle level. We can model the entire electric vehicle drivetrain. We can model the battery. We can model the effects of the structures and see how they provide shielding, and see what the radiated emissions is 5 meters away from the vehicle so that we can predict the total vehicle radiated emissions without requiring extremely complex or labor-intensive CAD cleaning to prepare for simulation. We can help with signal and power integrity. We can extract the S parameters for cables and connectors to be analyzed in follow-on circuit analyses. And then we can do radiated immunity. We can have a source outside the vehicle. We can predict the currents and voltages that couple to the cables and self-consistently predict how that will couple to circuits that we define in the Nexxim circuit solver. So we can do a full comprehensive end-to-end 3-solver coupling to see our EMC for radiated immunity. And then finally, we can predict cable and connector transfer impedance, which is very important for automotive cable suppliers. And conducted emissions, conducted immunity, again, we can route the cable harnesses through the vehicle, and by solving the cable harness self-consistent with the front end filters in the Nexxim Transient solver, we can have an end-to-end single model that does all of our CE/CS coupling. Okay, again, EMA3D cable has several advantages. We've got a solver that's had 40 years of validation heritage against measurements. It's integrated with a very user-friendly workflow inside SpaceClaim. Very importantly, we have a forgiving and rapid mesh to handle complex devices, and we can include all sources, all relevant enclosure or platform details, and all cables in a single model. All this with HPC technology that scales efficiently up to multiple cores across workstations and clusters. And by adding 3 new features, the Nexxim Transient Circuit Co-Simulation, the ability to export libraries of material properties and cable cross-section definitions, and finally to control custom terminations of cables and allow conductors to break out of shields, we've added to the features to expand what is possible and what can be modeled as we move toward the goal of doing all EMC testing via simulation to reduce risk and cost for EMC testing. Thank you very much for your time. I'm going to pass to Kaylin for questions and further discussion.
Thank you, Tim, for that informative webinar. Now let's get to the questions we've received. So the first question is the Nexxim circuit require, or does the Nexxim circuit require another license, or does it come with tool?
Yes, so the product Nexxim Transient Solver is included in EMA3D cable. When users purchase EMA3D cable, they get EMA3D, they get the M-harness cable transmission line solver, and they get the Nexxim solver all together as well as SpaceClaim. So you don't need to buy a separate license. You don't need to have another product. You just need EMA3D cable.
All right, next question. What are the steps to import from SI Wave?
Sure. So whenever we're running an SI Wave simulation, with just a few clicks, you can capture the near fields in SI Wave. And to do that near field simulation, literally it takes 60 seconds, 2 minutes to model the near fields. The user specifies the frequencies, they specify the distance away from the board, and SI Wave's near field simulation is really fast. And so you right click on the results and there's an option to export the near field data. And then in EMA3D, there's an option to import field data and scroll to the .and file format, which is SI Wave's file format, navigate to the .and file written out by SI Wave, and the fields will come in. So it creates a box in EMA3D. Then users with your mouse can drag that box and rotate that box into position in your 3D model. And then once you run the 3D simulation, those near fields will start to propagate, and you'll see that near field and far field coupling happen with your EMA3D platform.
All right, next question. Are the coupling efficiencies of cable configurations verified with tests, or are you using the test data as the coupling efficiencies of a cable?
Yeah, so both are possible. So EMA3D has the ability to specify um, the coupling efficiency of cables as an input. So that can be an empirical parameter. On the other hand, EMA3D includes models of cable shields that allows us to predict that coupling efficiency of cables. So it can go both ways in EMA3D. And then the third method is if you have experimentally measured coupling, users can input that data into the product. Now that said, we have a database of common types of shields. So those have been verified. They're good data. Um, However, if you don't see what you want there, you can bring that in empirically, or you can use one of the built-in analytical tools to calculate the coupling efficiency if you have something that is not already in the software product. And finally, if you don't like that analytical model, you don't see the cable you want, and you don't have the ability to measure it, EMA does offer a service to measure those cable coupling parameters. So if you can send us the cables, we have a services team that can do that service for customers.
All right, next question. What is the computational cost of the linked 3 solver path versus the previous simulations?
Sure. So essentially, the time step is linked between the 3 solvers. So you can only step as fast as the slowest of the 3. That tends to be the 3D solver. The simulation time for the transmission line solver is fast compared to the 3D solver, and both of them are fast compared to the circuit solver. So many times the impact is very negligible for those cables. So for many practical types of problems, it goes just as fast when you're solving the 3 together. If in some cases the impedance of the circuit is very low, in some cases in order to resolve the RC time constant of that area, sometimes we have to reduce the time step to resolve some very fast timing in those cases. So we will have to reduce the time step, but most of the time there's almost no impact.
All right, next question. Can you please share the documentation to train on the examples shown in the webinar?
Yeah, so within the EMA3D product itself, it's purchased, there's tutorials. So there's several tutorials there. There's also training material at the ANSYS Learning Hub. And then that training can be requested by reaching out to EMA at the contacts here. But essentially, the training will only be provided to active customers or demo customers.
All right, next question. Is this 2022 version released yet, and how do we get it?
It is released. It is available on the ANSYS customer portal. If it's not, it's supposed to be up by the end of the month. So I haven't checked if it's up today. If it isn't up today, it should be up maybe tomorrow or Monday. But that's the best place to get it. Or if you don't have access to the ANSYS customer portal, reach out through your ANSYS channel sales professional or your IT department to find out where you get access to the latest ANSYS releases.
Okay, next question. Can we import 3D data for cables directly from the Unigraphics NX?
Yes, so NX is a native format that we can pull into SpaceClaim. However, it's not incredibly common that NX defined cables typically are just the outer description of that harness and its path in 3D, which is very important. It is not common that the electrical connectivity, the wiring diagram, is stored in NX. So usually that has to be specified manually, or some companies prepare that data in wiring diagram databases like Zuken E3 or the Mentor Capital Harness tool. Those products can export a .kbl format. EMA3D cable can import that .kbl format. So whether your wiring diagram must be manually defined or it's available in a KBL format, there are ways to mate up that 3D NX information with the wiring information seamlessly in EMA3D. Both processes are very easy.
All right, next question. Are there reference papers comparing calculated and measured coupling efficiencies?
Yes, so EMA actually has published quite a bit of material on the validation of experiment compared to testing over the years. And actually, there's an ANSYS Advantage article coming out next month where a customer shows um, the good correlation between experiment and measurement. So keep an eye out for, I believe, February's ANSYS Advantage magazine for yet another EMA3D cable validation.
All right, next question, and I can actually answer this one. Will this recording and presentation be made available afterwards? It will. Everyone who has attended and registered for this webinar will be receiving the recording and the slides after the presentation is done. And then we'll go into some of our final questions. How has EMA3D cable been validated compared to measurement?
Yeah, so that's similar to what we said a moment ago. We've published many papers. Our customers have, and keep an eye open for the ANSYS Advantage article with yet another one coming in February. I don't want to give away the name, but it's an exciting customer testimonial.
All right. How long does it take to set up a typical simulation?
So EMA3D cable, it's really, if there's one reason to try this out, it's about the workflow. So some of these cables that I've shown today, you can set up in a single day. Some of these full vehicles can be set up in a matter of several days. We've taken what in the past might have been a multi-month research project and squeezed it down to hours or days. So we're really proud of the workflow we've been able to build.
All right, and our final question, what kind of computer resources are required?
Everything I've shown today can be run on an engineering workstation down to a laptop. So EMA3D does scale well up to large computational clusters, but you can get a lot of interesting engineering done on really large platforms with just normal multi-core engineering workstations, maybe $5,000 workstation.
Alrighty, it is time to conclude this session. As a reminder, any questions that we didn't get to will be addressed via email. You'll also be receiving an email from us with a link to the recording of this presentation, as well as the slides. If you have any questions about a particular section, please feel free to reach out through the EMA3D.com website or our email. Thank you for your time and attention, and have a great rest of your day.